Hi all, this is Mr. Yeager for chemistry, and we are beginning our short unit on equilibrium. We're going to be mainly looking at the idea that reactions can actually go in both directions. They can go from reactants to products and then actually products back to the reactants, and how we manipulate these to basically favor one side of the reaction for the other. Those are the two really main things that we're going to be looking at. We also will eventually look at obviously calculating out equilibrium and finding the concentrations of particular chemicals in the chemical reaction, but that will be in another video. So we're mainly just looking at, again, what is equilibrium and how can we affect equilibrium. Those are two huge parts to this particular standard. So moving forward, reactions can go both ways now. Okay, I have this good video from basically a North Carolina school here, NCSSM online, not my video, so theirs. But it's a good video to check out in terms of showing a reversible reaction, a reaction that can either move one direction or the other. So that's something obviously I show in my class. Again, up to this point, I have primarily showed my students where reactions are only in one direction, but they can go the opposite direction. Many of them can. There are certain ones that clearly prefer producing almost all products, but we can see some that go back and prefer to have some reactants left over or barely move at all. So, some things to know. There are reversible reactions, okay, where the products can react to form the reactants, all right? What's actually happening here is both of the reactions are occurring at the same time. There are reactants rearranging themselves to form products, while certain products are finding another one of the products and rearranging to form back into the reactants or decomposing back into the reactants. So both of these things occur at the same time. The thing is, based on how you have initially set up the chemical reaction, one side could be favored over the other side. We could have it where maybe you start out with all reactants. Well, if you start out with all reactants, clearly those things are going to zoom over and start forming products. They're going to rearrange, they're going to come into contact with each other. So that's going to occur maybe very, very quickly. But over time, these reactants, they start decreasing their concentration, their amount that they are. And so there's a lot more products then around than reactants, possibly. But at least we see that it slows down. What happens then is some of these products may then revert back into reactants. They might react with each other or, like I said, decompose or synthesize together to form back into the reactants. So over time, we start seeing this reverse reaction start building up, building up, building up. Well, of course, when there's reactants again, it continues to go back to products. So we get this endless cycle that happens between these two processes. When these processes eventually occur at the same rate, we have reached equilibrium. All right? This occurs when the rates of the reaction are equal to each other. That is important to notice because, like you see here, the big misconception is everybody goes, well, it's at equilibrium when everything's equal. That is not true, okay? It's possible, but I'm going to tell you the majority of problems we run into, we don't have equal amounts of products and reactants, okay? So equilibrium occurs when the rates are equal, not when the amounts are equal, okay? So that is not what we're looking for in the end. If they happen to be equal, fantastic, okay? But a lot of times they're not, all right? So, there are certain factors we have to take into account with chemical reactions, okay? Certain things we have to understand with it. To achieve equilibrium, I have number one written there again. Rate of the forward and reverse reactions are equal. Okay, that is really what we're looking for. The thing is, there are a couple little things that would have to happen. This is at a particular temperature. We're going to see equilibrium depends on temperature. So if I raise the temperature, we might see all of a sudden one side of the reaction occur more than the other, but then they'll find a new equilibrium. So we're going to learn about what are called equilibrium constants. These constants are based on a specific temperature and a specific pressure. Okay? So we have, what occurs there is we have temperature and pressure we usually will mention are at a constant, and then we want to figure out the concentrations at this particular equilibrium state. Now, pressure really is only important when gases are involved. Okay? Gases are the only state of matter really affected by pressure, because again, they don't necessarily have a defined volume. Okay? We can obviously manipulate their volume because there's all that space in between the gases. We cannot do that with liquids or solids. They're already compact. You can't make them technically more compact, really. Okay? So when we achieve equilibrium, it's at a certain temperature and a certain pressure, and you will come out to specific concentrations as well in the end. All right? So all of this stuff will come together. But again, I didn't say equal concentrations, I just said specific concentrations. Well, you will have this much of this product, this much of this product, this much of this reactant, this much of this reactant. All right? At that point, they're still reacting. They're still going back and forth, but the overall concentrations of them are essentially not changing anymore. Okay? Because it's occurring at an equal rate. So I already stated this. Solids and liquids are not affected by equilibrium because they're not affected by pressure, only gases, and their concentrations won't change in the end. Okay? And again, that's what we're talking about with the gases themselves. I can manipulate their volume, and therefore their concentration can get larger. I can get more particles in a little smaller space, obviously, than a larger space. Okay? So that's something we'll run back more on when we go to the calculating part of it. We basically ignore solids and liquids in the chemical reaction. They will not affect the equilibrium constant. All right, then we have this nice looking guy, okay? Le Chatelier's principle, okay? Le Chatelier was a scientist that worked with equilibrium, a chemist I should say, that worked with equilibrium situations. And what he basically came up with was this principle, which from his words is if equilibrium is disturbed by changing the conditions, the position of the equilibrium shifts to counteract the change to reestablish equilibrium. In other words, and we're going to go through the situations, he's just saying, we already have something in equilibrium, then you mess with it. There's going to be a shift either toward the products or the reactants to reestablish that equilibrium in the end. So with Le Chatelier's principle, it's very much a conceptual understanding of the chemical reaction itself and what equilibrium is going to do to help us figure out, well, are we going to shift this way or this way based on different types of disturbances, different types of factors that we're going to mess with. So what are those factors we're going to mess with? Okay? So the first one would be concentration. Okay? So I'm saying at a constant temperature, I should write at a constant pressure too. But if I mess with the concentration, all right, what do I mean by that? So I have my example down here. I have NaCl reacts with LiF. It's forming NaF and LiCl. This is how we draw equilibrium arrows. We show that this reaction's going both directions. Okay? So NaCl and LiF, quote unquote, are reactants, and NaF and LiCl are our products. We still write it that way, reactants on the left, products on the right, but they're constantly changing back and forth toward each other. Okay? So for concentration, guys, the big thing here is, again, we're technically saying right now everything is equal. Okay? Not equal, but the rate is equal. Everything is happy where it is. All right? When I mess with concentration, I basically shift the reaction to the opposite side. So you can see what I have written here. If basically I mess with the concentration, oops, I should probably adjust this a little bit. Sorry, I'm going to make an adjustment here. If we change the concentration of LiF, I have to correct something. I apologize here. I'm not going to go back and restart the video. But if I change the concentration of EF, I will make some sort of adjustment here. So I have to be a little bit clearer. What this is basically showing is if I increase the concentration of LiF, what I'm doing is I'm putting more pressure on this side of the equation. By increasing how much is in there, excuse me, I am now putting too many reactants in there, and the reaction is going to shift the opposite direction. Excuse me. So, if I increase the concentration, I can make this statement. If I increase the concentration of any of these chemicals, it's going to shoot to the other side. Okay, so I should reword this. If I increase concentration, it will shift to opposite side. Okay. I actually have that written there, so whoops. Okay, so I have that statement written right down there. If I decrease concentration, it wants to move to same side you're on. All right, let me try to explain that. What I mean there is, what happens where if I'm like, this is at equilibrium, but then I pull all the LIF out of the reaction. Well, now there's this emptiness on this side of the reaction, so what are the products going to do? They're going to go ahead and recombine and reorganize to make up for that missing amount of concentration that was on that side. So if I decrease concentration, it will shift to the side that I decrease the concentration. So if I decrease LIF, it'll shift toward the reactants of the equation. So let's kind of hammer this out again, because I made that little mistake with this wording here. I'm going to have to go back and correct that if you come back and check out my site. Okay? If I increase LiCl, what will happen? I will shift toward the reactants. If I decrease the amount of NaF I have, it will shift toward the products. All right? If I decrease the amount of NaCl, it will shift toward the reactants. Again, decreasing shifts toward the direction of where I'm decreasing it. And again, just think about the idea that it wants to fill up that space that it has. It doesn't want any more. That's why it shifts the opposite way if I increase, but it will shift in the direction if I take something out of it. Okay? So that is concentration. I believe I have my other two perfectly fine here. Pressure. Okay? With pressure, you basically have to pay attention to two things here. Okay? First off, pressure is only going to affect gases. Okay? Pressure is only going to affect gases. It doesn't affect liquids, aqueous, or solids. Okay? Gases are the things that don't like pressure. So if you raise pressure, you will push the reaction away from the gaseous side. Okay? You basically are saying these gas particles have to get closer together, so they're going to react more possibly. So gases don't like pressure. Raising pressure will push the reaction to the opposite side of the gas. Lowering the pressure will push it toward the gas. Okay? So again, we got to understand the vice versa as well. So in my reaction I have there of CO2 plus H2O produces carbonic acid on the other side. If I increase the pressure, here's my only gas, it's going to shift to the other side. Increasing pressure wants to get away from gases. If I decrease the pressure, we'll shift toward the reactants. Okay? So that's what we're looking at there. You can see my statement right there. Now, the confusing thing that might come out of this is, what if I have multiple gases on both sides of the reaction? Like the situation one is nice and easy because there's only a gas on one side. If you have gases on both sides, what it depends on now is how many moles of gases you have on both sides. And you look at the coefficients. The way you figure that out is look at the coefficients that you have there. Okay? Again, remember the coefficients represent moles that are reacting or being produced. So what I have in this reaction is there's 3 moles of gas on the reactant side and 2 moles of gas on the product side. So what you have here is there's more gas on the reactant side. So then the same kind of concept still applies. If I increase pressure, that's more gas on the reactant side. If I increase pressure, I'm going to support the products being produced more, because I want to relieve that pressure. I don't want to take up, there's too much stuff there. All right? So you look at how many moles, what are the coefficients, you add those up. It's not the size, don't count the atoms, that has nothing to do with it. It's all about the coefficients. Oops, let me circle the 2 there. All right? So again, because there's 3 moles of gas on the reactant side, 2 moles on the product, If I lower the pressure, I'll actually support the reactants because I can now have more space for them. Okay? So that is pressure. All right? Be very careful with that one. In relation to pressure, we will sometimes kind of trick, I'm not saying trick, sorry, I don't like using that word with it. Instead of saying I'm increasing or decreasing pressure, I might mention I'm changing the volume that this chemical reaction is taking place. What we need to understand is volume and pressure are inversely related. If I increase the volume, I'm going to decrease the pressure. If I lower the volume, if I decrease the amount of space those gases have, it's going to increase the pressure. This is something I'll cover later on, basically our last unit on gas laws, and we'll see about Boyle's law where volume and pressure basically act opposite of each other. So you got to pay attention here. If I say I lower the volume, I'm increasing the pressure. So what will then that do to the particular equation? So if I go back up to this one, to the one on the right, I'm going to use the tougher one. If I decrease the volume of the space that this reaction is taking place, that means I'm increasing the pressure. And because there's more particles, more moles on the reactant side, and there's higher pressure, I want to move to the product side. So decreasing the volume will increase the amount of products that is present there. All right? So that is the whole thinking behind it, the process behind it. The last one is temperature. Okay? For temperature, basically, we're looking again, there are obviously a lot of reactions either produce or take in heat. What we can do, and what you'll see happen, is we'll list heat as part of the chemical reaction itself. Clearly, it's not a chemical. But you'll see in like my example here, A plus B is in equilibrium with C, and heat is produced when C is produced. So heat is on the product side. So what I do with this is I treat it just like concentration. If I increase the heat, because that's on the product side, if I increase this, the reaction is going to shift back to the left toward the reactants. If I decrease the heat of this, then I want to reproduce that heat. So if I decrease heat, I'm actually going to shift toward the products because I want that heat to fill in again. All right? So temperature, treat like concentration is the biggest thing I can kind of say there with it. So if heat's on the other side, we'd have to do the opposite with it, you know. Don't forget, we have mentioned this before, there are what are called endothermic and exothermic reactions. So I might not list heat in the chemical equation, and you have to be able to identify, and you can write it in yourself. If I say it's an endothermic reaction, heat is on the reactant side. When I say exothermic reactions, heat is on the product side. All right, so be prepared for some of those. So let's take a look at a couple other examples here. Okay, I guess I'll start with this one. I have two examples. So let's go through all the different situations I can have here. All right, let's say for instance that I increase the concentration of H2. Okay, increase the concentration of H2. If I increase the concentration of H2, I'm going to shift this reaction toward the products. Why? I'm putting more stuff in on the reactant side, so it wants to relieve that pressure and go on the product side, according to Chatelier's principle. Okay? Let's say I decrease the concentration of CH3OH. If you haven't learned yet, the brackets around a chemical, that means concentration. Let's say I decrease the concentration. That means I'm opening up more space on the product side. Guess what? I'm going to shift toward the products. Again, I was trying to play around with you there and trying to say, hey, we're always shifting toward the products. It's just the situations I'm given. Okay? All right. What about if I decrease pressure? If I decrease the pressure? Well, you can see everything is gases here. But there are 3 moles of gas on the reactant side, 1 mole of gas on the product side. If I decrease pressure, I'm creating more space. That will shift toward the reactants. All right? If there's less pressure, I can produce more gas. All right? Let's say that I decrease the temperature. If I decrease the temperature, I need to look for heat now. Here's heat on the reactant side. Since I'm decreasing temperature, I'm decreasing the amount of heat, so I need to reproduce that, so that's going to move the reaction toward the products. Okay? So those are some good examples there. I'll do one more here. This one is not balanced. I have to balance the reaction first. I need 5 here and 2 here and then 2 there. So, sorry, I didn't write the states of matter here. Here's gas and here's gas. Okay. So for this one, let's play around with it again. Let's say I increase the concentration of N2. That means I'm going to shift toward the reactants. Let's say I decrease the concentration of O2. That'll shift my reaction toward the products. Concentration, it always moves toward the product, or if it decreases the concentration, it always moves towards the thing you're decreasing. All right? I can't do a temperature one on this. I don't have heat in here. I didn't say whether it's exo or endothermic, so that's not going to be asked. But then I can talk about pressure or volume. Let's say I increase, or let's say I decrease the volume that this reaction is occurring in. If I decrease the volume, I am increasing the pressure. So if I increase the pressure, I want to go toward the side with less gas. Well, I have 2 moles of gas on the reactant side. I have 7 moles on the product. This is clearly going to go toward the reactant. I need to go toward the lesser amount of gas. All right. So, sorry about that little confusion with concentration initially. I think we cleared it up. But we have gone over Le Chatelier's principle and basically you can see not a lot of math being done. It's more about understanding what's happening in equilibrium when the rates are the same for both the forward and reverse reaction, and then what would happen if we disturb that equilibrium through concentration, pressure, volume, or temperature. All right, so that's it for now. Thanks.